Following Broadcom's buyout of VMware, many organizations have been evaluating their virtualization strategy. The options fall into several categories. The first is running VMs on Kubernetes with solutions like KubeVirt. The second is migrating to open source hypervisors like Proxmox. The third is moving to private cloud platforms such as OpenStack. Or the fourth, which is shifting to managed infrastructure with cloud providers. For teams that have chosen the Kubernetes path, whether through KubeVirt or other VM on Kubernetes solutions, the follow-up question is often this: now that we've moved our VMs to Kubernetes, what comes next? That's what we'll address in this video. We'll start from a position where VMs are already running on Kubernetes through KubeVirt, and we'll demonstrate the next step, evolving those workloads to run as native Kubernetes pods. This is cloud-native modernization, which means running applications as containers with Kubernetes managing their lifecycle. It's a natural progression after infrastructure modernization. The challenge many teams face isn't technical capability, it's knowing how to bridge from VM-based operations to cloud-native patterns without disrupting production. Three key questions often come up. First of all, how do you containerize existing services safely? Secondly, how do you migrate traffic with zero downtime? And thirdly, how do you validate that the migration delivers the expected benefits? We'll demonstrate a practical approach using a real e-commerce application. Our demo environment uses KubeVirt to manage VMs on Kubernetes, but the containerization and migration patterns we'll show apply regardless of your starting point. We'll cover three main areas. First of all, how to containerize services properly. Secondly, how to implement cloud-native observability and security. And thirdly, how to execute migrations with proper risk management. First, let's establish what changes when workloads move from VMs to containers. When services run in VMs, we manage complete operating systems. This includes boot sequences, init systems, package managers, and the entire Linux stack. Resource allocation happens at the VM level, so scaling a service means scaling everything inside that VM. Startup times are measured in minutes, and troubleshooting means SSHing into boxes to hunt through logs. With containers, we package just what the application needs to run. Startup times drop to seconds, resources are allocated at the service level, Kubernetes handles placement, scaling, and health management automatically, and operational visibility improves through structured logging and metrics endpoints. The resource efficiency differences are significant. When services run in VMs, resources are allocated for the entire operating system stack. With containers, resources are allocated just for what the application needs. For our demo today, we're working with a typical e-commerce application split across two VMs. The services are distributed based on whether they're front-end or back-end. The application state lives in Redis on the back-end. Both VMs are managed by KubeVirt as VM pool objects, which lets us deploy duplicate VMs as needed. But this scaling capability is far from ideal because we're still working with VMs. If a service needs more capability during peak traffic, we need to scale the entire VM, bringing along services that don't need additional resource. VM boot times make it difficult to scale during traffic spikes. Individual service metrics are hard to see, and troubleshooting means SSHing into VMs and hunting through logs. When we migrate these services to containers, the experience will get much better for both customers and maintainers. Now, we're not going to rip everything out and just start over. We'll migrate one service carefully to prove that this approach works. Our first step is to decide which service we'll migrate first. We'll evaluate this on four criteria: technical simplicity, low blast radius, measurable impact, and team readiness. In this instance, the currency service is a good candidate. It ticks all the boxes for these reasons. First of all, it's technically simple. It's a Node.js service which converts currencies using European Central Bank exchange rates. It makes external API calls, but doesn't manage any complex state. It doesn't require any distributed transactions, consensus algorithms, or database migrations, so containerization should be fairly straightforward. Secondly is low blast radius. It's not on the critical payback path. If it breaks during migration, checkout might slow down, but sales will still continue. Thirdly is measurable impact. It outputs metrics which we can use to track response times, conversion rates, resource usage, and error rates, so we'll know immediately if the migration is working or not. And lastly is team readiness. The team already knows containers and can handle the application refactoring needed for containerisation. We're also confident that this team can push changes as needed and not block the project. What we'll show in today's demo is just part of a wider journey to containerisation. Our starting point for today's demo is an online store running on VMs on Kubernetes, with Portworx handling the storage layer. We've got the foundation in place for workload modernization, but we're not actually using any of the Kubernetes features like auto-scaling, health checking, or rolling updates that make it worth the complexity. Our endpoint for today's demo is a hybrid architecture with services running in a mixture of VMs and containers. We'll extract the currency service from the backend VM and run it as a native Kubernetes pod. Everything else will stay in VMs. All communication is done seamlessly through Kubernetes service discovery. We're using this hybrid approach on purpose, as it lets us test containerization on a single service before changing anything else. You'll learn something new about your system each time you migrate a service. The eventual goal is full containerization. Each service will run as a Kubernetes pod that can scale discretely and independently. Redis will also be moved to a pod, but because Portworx provides distributed storage with replication, we won't need multiple Redis instances for application data to be highly available. But today we'll focus on that crucial first step of proving that the migration pattern works. We'll walk through building a production-ready containerized service, migrating live traffic with zero downtime, and then show how we can validate the results. At each step, we'll build on cloud-native principles that we'll explain as we go. This demo covers about 3 to 4 weeks of work in a real project. 1 week for containerization, 1 week for testing and validation, and 1 to 2 weeks for migration planning, execution, and post-migration evaluation. We'll condense this down for you to show you the key decision points and technical steps. Right, so before we start writing code, let's talk about strategy. We've already mentioned that we'll be using a hybrid model to run the VMs and pods together during migration. While this approach will generally help us reduce risk and learn as we go, it's equally important that we make sure human error does not creep into how we manage the infrastructure. One way in which we can reduce this from happening is through the use of GitOps with Helm charts. For this demo, we're already using this to manage our VM infrastructure. Think of Helm like Terraform or Ansible, but instead of managing network configurations or VM templates, you use it to manage application deployments. Like Kubernetes, it's declarative, which means you say what you want to run rather than how to run it. It supports version control, so every change can be tracked in Git. And it's environment aware, using variables to customize deployments for dev, staging, or production. Right now, our Helm chart currently creates 2 VM pool objects, which define our VMs and their resources. We also use this chart to manage the networking that makes it possible to discover our pods and VMs inside a cluster. Right now, the Kubernetes service for currency resolves to the IP address of our backend VM. During migration, we'll update this service to point to the containerized pod instead. Because the front-end applications only care about the currency DNS name, they won't know that anything has changed. How this works under the hood is fundamental to our migration approach. In the VM world, when backend servers change, you typically have to manually configure a load balancer like F5 or HA proxy. Kubernetes services work the same way in concept, and you can think of them as automated internal load balancers. Instead of manually updating a server list, you instead add labels to the target workloads, and services will automatically route traffic to anything matching these labels. It's like telling your F5 to send traffic to any server with the role equals web label, but Kubernetes will update the list automatically as containers start, stop, or fail health checks. To facilitate this under the hood, Kubernetes creates what are called endpoints. Think of these as the list of servers in a load balancer pool. These show which target IP addresses are currently healthy and receiving traffic. When we perform our migration, we'll do this by updating the services selector. Once this is done, these endpoints will automatically switch over from VM IP addresses to the pod IP addresses. To facilitate this migration process, our Helm chart will use conditional logic to deploy either VMs or pods based on the configuration values we provide. Rather than rewriting how we deploy our infrastructure, we're extending it. Instead of rebuilding our existing GitOps pipelines, approval processes, and rollback procedures, we can simply build on top of them. And by continuing to enforce these procedures and pushing changes using infrastructure as code, this structure allows our processes to succeed at scale and maintain that level of consistent quality. Now that our strategy is clear, let's look at the framework we will follow for these migrations. Here at Livewire, we have expertise in helping teams through these sorts of migrations. We've learned that technical work is only half the challenge. The other half is managing the organizational change and risk. That's why we've developed our workload modernization roadmap. If you've worked with change management, you'll recognize the approach we're taking. We break down complex infrastructure changes into managed phases with clear gates between them, similar to how you'd manage a major server migration or data center move. At each step, we outline which teams should be involved, as they will be the stakeholders for that particular phase. Our roadmap follows established project management principles, but tailored specifically for containerisation projects. First of all, we align with stakeholders and establish success criteria. Then we design a technical approach and map dependencies. We build and test the containerized services, execute the migration with proper rollback plans, validate the results, and finally hand over to the operations teams. This systematic approach prevents a common mistake, which is treating infrastructure changes as only technical work. Like major system implementations, these projects typically fail due to poor change management rather than technical issues. The key insight is that each migration teaches you something about your environment that you didn't know before, similar to how phased server migrations reveal application dependencies that weren't properly documented. By the time you've migrated your 5th service, you'll understand how to spot hidden dependencies in applications, where your configuration management is inconsistent, and how to spot when teams will need additional training on container troubleshooting. This organizational learning approach is why we don't recommend migrating everything at once, even when it's technically possible. You'll learn from each step to make the next one smoother. Now, this framework covers everything from initial alignment with stakeholders through to the final handover, but in today's video, we're focusing on the practical implementation of 3 specific phases. The first phase is to build. This maps to the design and build phases in our framework. We'll show you how to containerize your service, implement application best practices, add observability with structured logging and Prometheus endpoints, and integrate with Kubernetes security frameworks. The second is migrate. This maps to the execute phase. We'll demonstrate the actual traffic switchover using our service discovery approach, show you how to update runtime configuration without downtime, and validate that the migration was completed successfully. The third is validate. This maps to the validation and analysis phase. We'll compare performance metrics between VM and container deployments, evaluate the operational complexity of running hybrid workloads, and document lessons learned before scaling this approach to remaining services. With the framework context established, let's put this structured approach into practice. Our first step is validating that our existing environment is ready for the hybrid model we've outlined. Before we dive into containerization, let's confirm what we've established from Demo 1 and our planning work. So our hybrid deployment strategy is confirmed, so this means PMs and pods will coexist during migration. Our existing Helm chart will support both VM and container deployment. Our service discovery layer is ready for traffic redirection. We've selected our target service using our 4 criteria framework. Our GitOps pipeline remains unchanged throughout the migration, and our cluster has sufficient capacity for running duplicate services during the transition. With our framework context established and our environment validated, it's time to start the actual containerization work. Most of our design phase work was completed during the KubeVirt migration. So we set up the cluster infrastructure, we added GitOps with Helm, and proved we could run production workloads. Now we need to validate that the cluster is ready for hybrid deployments. We need to check we have enough cluster capacity during migration, because we'll be running the concurrency service in both the VM and as a container at the same time. We need enough spare capacity to handle additional pods without it affecting the existing workloads. Once that's confirmed, we can then move on to the build phase. When we containerize applications, we follow patterns that well-designed services should typically already use. The industry calls this the 12-factor app methodology, but ideally, these aren't new requirements that you need to add to existing services. Let's go through the three factors that will matter the most for our currency service. The first factor is configuration externalization, which is about making sure any changeable values are managed sensibly. Most well-designed services already keep configs separate from code. They should be reading settings from files or environment variables and not hard-coding values. Containerisation uses environment variables for all config, which will make deployments simpler. The second factor is stateless processes, which is about making sure your apps run with as few dependencies as possible once they are in runtime. Examples of this include if your service can run behind a load balancer without sticky sessions, or if your service doesn't write critical state data to local disk. In these instances, we should be able to restart the service without data loss. If you want to take full advantage of Kubernetes' ability to quickly shape your live application fleet, it's crucial that your apps are able to restart safely at any time. The third is port binding, which is about making sure your apps can be segmented and available through predictable port numbers. Now let's talk about creating the container image itself and go through some of the key differences in how these are built compared to VMs. When you build a VM template, you start off with a full operating system, which includes the init systems, package managers, system services, and all needed server administration tools. Containers work differently. They're designed to run a single application process and not be managed as a complete system. Let's have a look at what this means in practice. Here are 3 Node.js base images. When you build your application's container, you'll usually build it on top of an existing base image. The first base image contains the full Ubuntu system. The second image contains Debian and uses only the essential packages. And the third contains Alpine Linux with minimal libc and Node.js runtime. For production uses, Alpine or distroless is usually the best choice, since it has a smaller attack surface and a faster startup time. But this is just one way in which we can improve the container build. Another is through the use of multi-stage builds, which let us separate the build environment from the runtime completely. During the build stage, you have full access to the dependencies, compilers, build tools, and source code you'll need to complete the build. We don't need these once the build is done, however, so for the final image, you can copy over just the compiled application and anything else it needs during the runtime. Our last step in finalizing the container build process is satisfying any security requirements. This means non-root user execution, adding proper signal handling for graceful shutdown, adding built-in health checking, and any additional work needed to minimize the attack surface. See how the image size has decreased as we've improved the container build process. Our original build with the dev base image was over 1 GB, which was reduced to 200 MB, and then further down to 165 MB. The currency application itself hasn't changed here, we've just improved how the deployment is packaged. Of course, we need to make sure the container starts cleanly and responds to health checks. Once we're confident this is done, the next step is to integrate this container with Kubernetes capabilities to make it production ready. To get our service initially running in Kubernetes, we'll need 2 basic objects, a deployment which contains a pod specification, and a service to enable internal DNS discovery. Before we dive in, let's go over again how services work and look at the configuration we'll use for the currency service. This is a load balancer configuration. It says to Kubernetes, create a load balancer called currency service. If it receives traffic, forward the traffic to port 7000 on any pod with this label. The actual server list is maintained by Kubernetes in a resource called an endpoint. These show which IP addresses are healthy and receiving traffic. Instead of manually adding and removing servers like with F5, Kubernetes will update this list automatically when pods start, stop, or fail health checks. Once this service exists, any workload in the cluster can reach our currency service using the DNS name. Under the hood, the request flows through core DNS for name resolution, then to the service object, which consults the endpoint to find healthy backend IP addresses, and finally reaches the Vert launcher pod hosting our VM. Let's look at how the configuration handling has evolved from VM-based config to more cloud-native patterning. Here's how the VM service currently handles config. It has complex file parsing with multiple fallback locations, custom configuration formats, file watchers for live reloading, and deep object merging. Here's how the containerized service manages its config. The container service simply reads from a single file and sets sensible defaults where necessary. Most well-designed services keep configuration separate from code. The VM approach often uses complex file systems. Containerization uses environment variables instead, so this will make deployment simpler. In Kubernetes, we provide configuration through config maps or through the pod specification. Think of config maps like centralized configuration files that multiple containers can share. Maintaining good configuration practices in theory should be the same across VMs and in containers. You only want to change where the configuration comes from, not how your application reads it. Once configuration is complete, next we need to provide proper monitoring and troubleshooting capabilities that we'll need in production. We're not replacing any existing monitoring tools. We're adding application monitoring that works with your current systems. The patterns follow the same monitoring principles you already know: collecting logs, exposing performance metrics, checking service health, and alerting when any problems occur. The difference is that instead of configuring separate agents, we'll build these monitoring features into the application packaging. The first aspect of this is structured logging. Let's look at an example. To add logging to the VM version, it requires over 200 lines of custom logging code to implement log rotation, directory creation, log compression, and any cleanup jobs we need. In the container version, we'll use a JavaScript logging package called Pino that writes structured JSON to standard out. This structured format matters because it allows any downstream logging system to parse, filter, and query log entries as data rather than text. You can search for specific transaction IDs, filter by log level, or extract custom fields without writing fragile regular expressions. Kubernetes is able to automatically create these logs and send them to your logging system, so you don't need to install and maintain separate shipping agents. This works with Splunk, Elasticsearch, or other tooling. The second aspect we'll look at is metrics endpoints. Let's look at an example. In Kubernetes, instead of performance counter agents scraping system metrics, applications can expose a HTTP endpoint that Prometheus can scrape. This is like having your application provide its own performance metrics through a web interface. Prometheus works like SCOM or Nagios, but instead of installing push agents on each server, it pulls metrics from HTTP endpoints. Each service is expected to provide its own monitoring data. The third aspect is health checks. In the VM world, you typically use external monitoring agents or scripts to check if services are responding. Kubernetes builds this health checking directly into the platform, continuously validating that your application process isn't just running, but is actually ready to handle any requests. Without health checks, Kubernetes will mark our currency service pod as running when the process starts, even if the gRPC server isn't ready yet to accept connections. Kubernetes provides 3 types of probe. The startup probe gives the service time to initialize before Kubernetes can kill it off for being too slow. The liveness probe detects if the service has deadlocked or crashed and triggers a container restart if this is the case. And the readiness probe will cause any unhealthy instances to be removed from the service endpoints temporarily. No changes are made to the pod itself, and the pod will receive traffic again if it is able to get back to a healthy state. Let's take a look at a practical example of how we implemented this and how the health checking has evolved from VM-based to cloud-native. The VM version has no health checking built into the application itself. Instead, it relies on an external bash script, which is implemented using hard-coded paths and PID files, file-based state tracking between runs, port scanning using netstat, HTTP endpoint probing with a complex retry logic included, and alert mechanisms which will try to restart the service via systemd. Our currency service communicates using gRPC, and ideally our health checks would use the same protocol. For health checking, Kubernetes 1.24 introduced baked-in native gRPC probe support, which makes it even easier to add health checking to our service. In this instance, we can implement standard gRPC health service, so instead of providing HTTP health checks, we can health check using the same protocol stack. Our health check validates actual service capability. This prevents routing traffic to instances with stale exchange rate data when the ECB API is unreachable. This means we can create Kubernetes native startup, liveness, and readiness probes without having to create separate HTTP endpoints. The pod doesn't receive traffic until it's genuinely ready, and if it becomes unhealthy, it's automatically restarted or removed from the load balancer. Most production services should already handle shutdown signals appropriately to ensure in-flight requests aren't lost. Containerisation makes these patterns more explicit, with the Kubernetes pod lifecycle providing clear and defined timelines. When shutting down a pod, Kubernetes allows a 30-second window by default for graceful shutdown to occur. The pre-stop hook allows connections to be drained before the host machine sends a SIG-term signal to initiate the pod teardown. Here is how we've implemented the shutdown logic in our currency service. We've added a pre-stop hook that is executed in the container when pod termination has been triggered. Watch what happens when we do delete the pod. First, Kubernetes sends a SIG-term signal. Our application will then immediately log that it's received the shutdown signal and begin its graceful shutdown. Any existing connections will drain, and the gRPC server closes cleanly. Now when Kubernetes needs to restart or scale your pods, the application shuts down cleanly without dropping requests. Now that we've had a look at adding Kubernetes native observability to the app, the next thing we should do is ensure that our service meets production security requirements. We can do this using some Kubernetes security frameworks. These frameworks work in tandem with current security systems in the operating system. They enforce the same security rules that you already use for VMs, except for containers instead. One of these frameworks is pod security standards, which work like group policy in Active Directory, except for containers. Just like you have different group policy objects for domain controllers, web servers, and workstations, pod security standards have 3 profiles. The first is the privilege profile, which allows an app to have local admin-like access. The second profile is baseline, which allows an app to have standard user-like access with specific permissions. And the third profile is restricted, which enforces maximum security. The difference here is that enforcement takes place when you create the deployment in the cluster, not when users log in. In this example, we'll enforce the restricted profile since this is a production setting. This means that containers must run as non-root and can't do anything dangerous. When we try to deploy a pod that breaks these rules, such as running as root or requesting dangerous permissions, Kubernetes will block it immediately. To make our deployment compliant, we need to ensure that the pods run as non-root, drop all Linux capabilities, and that we disable the ability for the container process to perform privilege escalation. Another framework we can use is network policies, which work like Windows firewall rules and can be defined as code and applied automatically. In a Linux setting, network policies are translated into IP tables rules by compatible CNI drivers. Here's an example network policy we could use. This policy ensures our currency pod only accepts gRPC traffic on port 7000 inside its namespace, whilst allowing outbound HTTPS to allow it to send any external API calls if needed, or query DNS for service discovery. These are just some of the Kubernetes best practices we've covered. To get a complete set of production-ready manifests, we need to make sure we've covered all of the cloud-native best practices. So before we continue, we need to make sure that we have a non-root user configured, that configuration is externalized using environment variables or config maps, that we've added structured logging to standard out, that we've added gRPC health check endpoints, that Prometheus metrics are being exposed, that the workloads are pod security standards compliant, that resource requests and limits have been set, and that network policies have been configured. We also need to make sure that all these changes have been added to the manifest correctly and that the cluster won't reject them when they're deployed. We can test this using a server-side dry run, which validates against the actual cluster state and policies. This checks against resource quotas and limit ranges in a namespace, admission controller policies, including the pod security standards we enforced earlier, API server validation rules, and custom admission webhooks. If the server-side dry run passes without errors, then the currency service is ready for deployment. But remember, our actual source of truth isn't these static manifests, it's our Helm chart. So before we deploy anything, we need to validate that our Helm templating is correct and will generate the manifests we expect when we run the actual installation. This means we need to treat any Helm chart changes just like any other infrastructure change, just like how we would validate with Terraform plan before changing any Terraform state. When we run the Helm install, this will create our deployment, service, config map, and any other supporting objects. If we watch the pod startup sequence, we can see our currency pod progressing through the different startup phases: pending, then container creating, and finally the running state. If the pod is reporting ready 1/1 status, this means our health checks are working. To get here, Kubernetes has pulled the image, started up the container, connected the pod with the rest of the cluster networking, run the startup check, and confirmed that the readiness check passes. This is just one working example of Kubernetes lifecycle management in practice. The platform works continuously to ensure your service remains healthy and available by monitoring pod health and handling failures automatically, all without manual intervention. Now let's check how our service discovery architecture is doing and verify if it is ready for us to perform the cutover. Our existing currency service is currently pointing to the backend VM, and our new currency service that we have been using for testing is pointing to the currency pod. During the cutover, we'll update the selector for the existing currency service to point to the pod instead. You can see the two endpoints which show the actual IP addresses that the two services currently route to. You can see the current service is pointing to the backend VM's IP address, and the new service is pointing to the pod IP addresses. When we do the traffic cutover, the endpoints in the current service will change from the VM IP address to the pod IP addresses. The service name will stay the same, so any API calls from the front-end service will continue working as before. During our testing of the currency pods, we can see that health checks are passing, logs are showing successful startup, and we see no errors in the logs or the events. However, before we switch the traffic over, we need to do one last thing. We need to create performance baselines so that we can compare how the currency service performs before and after we containerize it. We're using a load testing tool called Locust to simulate realistic e-commerce traffic patterns. The load generator does the following. It browses products, it adds items to the cart, it performs checkouts, and it makes currency conversion requests. This mirrors actual customer behavior, so we can see how the service performs under production-like conditions. Let's have a look at what the metrics show us. First, the VM-based currency service. Under our load test, we can see the service is responding, but with some interesting characteristics. Now let's compare this with the containerized version. The pod is handling the same request patterns, but we can already see some differences in how it's behaving. These baseline numbers tell us several things. First, response times have improved significantly, particularly in the 95th percentile, where users notice slowness most. Secondly, resource efficiency has increased. The container uses a fraction of the memory and CPU compared to the VM-based deployment. Thirdly, startup times have dropped, which means faster scaling and recovery. We can also access detailed metrics from the Prometheus endpoint we built into the service. This shows us request durations, success rates, and cache hit ratios in real time. Our Grafana dashboard is monitoring both deployments simultaneously. This gives us visibility into metrics like request latency, error rates, and resource consumption across the hybrid environment. When we switch traffic, we'll watch these dashboards to confirm the migration is behaving as expected. What these baselines do establish is our success criteria. If the containerized service maintains these performance characteristics once it receives production traffic, we'll know the migration has succeeded. If we see degradation, we'll have clear data to guide our troubleshooting or rollback decision. Before we switch any production traffic, we need to validate that everything is genuinely ready. This is our go or no-go decision point, so we need to check the following. We need to check that the currency pod is healthy and passing its health checks, that service discovery is configured correctly for both VMs and container endpoints, that performance baselines show the expected improvements, that monitoring is capturing metrics from both deployments, that our rollback procedure is tested and ready, and that the on-call team has been briefed and is ready to help if needed. With everything validated, we can proceed to the traffic switchover. Before we demonstrate the technical steps, let's establish what we're actually changing. At this point in the migration, we're making a single configuration change in the service discovery layer, updating the selector to route traffic to the containerized service instead of the VM version. Similar to updating a load balancer to point to new servers or changing DNS records to redirect traffic, this is a routing change rather than an application change. All of the work to build, deploy, and test the currency service as a pod has been safely completed in isolation up until now. The pods are running, health checks are passing, and monitoring is working. What remains is directing production traffic to them. The actual migration is straightforward. We run a Helm upgrade with new values. This updates the selector labels, immediately redirecting all traffic from the VM to the pods. And that's it. The front-end applications will start sending conversion requests to the currency pod. Because the DNS name is unchanged, the front-end services themselves won't need any configuration changes. They'll continue calling the same service name, unaware that the back-end implementation has shifted from VM to container. With Kubernetes service discovery, we don't need to worry about DNS propagation delays. The endpoint is updated immediately, shifting the load balancer pool members from the VM IP address to pod IP addresses. Now we're in the validation stage of our execute phase. Having executed traffic, we need to confirm 3 critical aspects. Traffic is reaching the containerized service, the service is responding correctly, and Kubernetes is managing the workload as expected. First, let's verify traffic flow. If we tail the logs using Kubernetes label selectors, we can see structured JSON entries showing incoming gRPC requests with request metadata, conversion details, and response times. Next is functional validation. We can directly test the gRPC endpoints to confirm the service is responding correctly. The currency conversion results confirm the service is functioning correctly. Our European Central Bank exchange rate integration is working. Conversion logic is accurate, and response times are well within acceptable bounds. Now let's examine resource utilization. The horizontal pod autoscaler we configured is actively managing our deployment. Based on CPU utilization thresholds, Kubernetes has scaled our initial single pod to multiple pods. Our Prometheus metrics endpoint is functioning correctly, exposing application-specific metrics like currency conversion counts, cache hit rates, and ECB API response times. These custom metrics provide visibility that was difficult to achieve with the VM deployment. During this validation phase, you would typically have your monitoring dashboard open, watching for any anomalies in request latency, error rates, or resource consumption. In this instance, all indicators confirm the migration has been successful, and we can proceed with confidence. The advantage of the migration approach we've used is that if we need to roll back this process and move production traffic back to the VM, the rollback change is just as simple to apply. All we need to do is update the Helm values to change the selector back to the old label. We can do this either by deploying a new Helm release or by rolling back to a previous Helm release. If we know the last known good Helm release, then a Helm rollback can be a good break glass to revert the service selector back to the VM. This is useful when a code change will take too long. During the transition, we can monitor both container and VM logs simultaneously. The single service approach gives us a clear on-off switch. Traffic will go either to the VM or to the container, with no confusion about which service name the application should be using. The migration is technically complete. Our currency service is now running as a pod whilst front-end and checkout remain in VMs. But before we call this successful, we need to validate the results. This is where the validation and analysis phase of our framework becomes critical. We need to confirm that the migration has achieved what we intended. We need to validate 6 key aspects. First, that we achieved 0 downtime during the migration itself. Second, that no customer-facing errors were introduced. Third, that performance metrics show improvement compared to our VM baseline. Fourth, that operational workflows are now simpler using standard Kubernetes tooling. Fifth, that our rollback capability works as designed. And 6, that monitoring and observability are functioning correctly. Once we've confirmed all 6 criteria, we can now say this migration is complete and successful. This first migration proves the pattern works. More importantly, it gives us insights for improving the process. From this first migration, several lessons emerged. If we start off with a stateless service, this makes containerisation straightforward. Helm's logic allowed for safe parallel deployment. Service discovery made traffic switching instantaneous, which meant pointing the existing currency DNS to the pods was easier than changing the endpoint in the front end. Monitoring both the VM and containers simultaneously reduced risk, and having clear and tested rollback procedures gave us the confidence to proceed. And that was a working example of how to gradually modernize applications from VMs to cloud-native patterns in Kubernetes. We've just walked through the design, build, execute, and validation phases for a single service. This same framework applies whether you're migrating your second service or your 20th. The hybrid approach we've demonstrated isn't just about reducing risk, it's about learning as you go. Each migration teaches you something new about your application stack, your team's capabilities, and your operational procedures. After migrating 10 services, you'll have deep knowledge of what works in your specific environment. Following this framework means your 10th migration will be significantly faster than your first, with documented patterns, tested procedures, and a team that understands the process. We've shown one service migrating from VM to container. Depending on where you are in your modernization journey, your next steps might be containerizing additional services. Or, if you're still on traditional hypervisors, you might first need to move these VMs onto Kubernetes. If that's your current challenge, we've got a separate video demonstrating one VMware to KubeVirt migration path using open source tooling. Finally, if you're working through similar migrations and need help, reach out to us at lwy.io. Thanks for watching, and we'll see you in the next video.